This lesson is focusing on drawing and naming ionic bonds. Remember, an ionic bond is between a metal and a nonmetal, and we'll be transferring electrons. So with ionic bonds, the important thing to always start off with is always to look for a metal and a nonmetal. So again, metals are on the left-hand side of the periodic table, left of the staircase, and nonmetals will be on the right-hand side of the staircase. Because metals have between 1 and 3 valence electrons, it's much easier for them to lose those 1 to 3 valence electrons than it is for them to gain. So metals will always form a cation, whereas nonmetals are going to have between 5 and 8 valence electrons. So it's much easier for them to gain electrons than it is to lose. So they will always form anions. So with ionic bonds, the important thing is to remember the octet rule. All atoms want to have a full outer set of electrons. So in order to do that, they must meet the octet rule where they have 8 valence electrons. So this particular atom right here, this is fluorine, it's going to gain 1 more electron to meet the octet rule. And this one right here is lithium, which has 3 electrons, 1 valence. So if it loses this electron, then we'll be left with 2 in its outer orbital. Now remember, the first energy level is full when it has 2 valence electrons. So it's actually meeting the duplet rule, which is showing that its outer energy level is full. So both of these are meeting the rules here. Important thing to remember also is that when they gain and lose electrons, they're going to be forming charges. So fluorine, when it gains an electron, this makes it an anion, and we're going to end up with a -1 charge. Whereas lithium right here is losing this one, so now we ended up with a plus charge. So here's one dealing with sodium chloride. Sodium has 1 valence electron, and we'll show that with our electron dot diagrams. This is the simplest way to show it. And chlorine has 7 valence electrons. Sodium would like to get rid of the 1, and then chlorine would like to gain 1. So when you do that, when you look at the actual structures right here, this valence electron is going to transfer over. And when you do that, you're going to get a +1 charge and a -1 charge. And if you think back to physics, opposite charges will attract. So you're going to get sodium and chlorine attracting to each other, and this is what the bond is. So there's not a physical bond actually holding sodium and chlorine together. It's opposite charges. It's like having static electricity holding 2 socks together that run through the dryer. Important thing to remember when you're dealing with both ionic bonds and covalent bonds is the number of valence electrons. Again, valence electrons are the electrons in the outer orbital. So group 1 always has 1 valence electron. Group 2 has 2. Group 13, if you drop the 1, you'll have 3, and we'll get to 4, and so on. We're going to end with 8 valence electrons, so 8 is your maximum number. And when we're working with these, we also want to identify their charge, which we've been calling the oxidation number. So in order to do that, we look at group 1, and they have 1 valence electron. Basically, it's 1 extra one, so we'll put +1 to say we have an extra. Group 2 has +2. Group 13 is +3. In the middle, we can go either way. It's easy for them to gain and lose those electrons, so we'll put + and -4. Group 15 is -3. Group 16 is -2. Group 17 is -1. And 18 is 0, because they don't want to gain or lose any. So again, we're counting from +1 up to 4, and then from 4, we'll count back down to 0. So you want to learn that pattern so you can pull these elements out quickly and know their valence electrons and oxidation numbers without having to think too much about it. So there are some rules when we're dealing with ionic bonds as far as forming the formulas. The first thing we always have to do is identify that we're working with a metal and a nonmetal. Second, you want to write the symbol with their charges, which is their oxidation number. 3, we want to cross over the charges from top to bottom. And 4, we want to reduce the subscripts and remove any 1s. So if we're looking at these, I've already put the charges in for these. I would not necessarily have to do that because the charges are constant. So you'd look on the periodic table, and all I'd really have to tell you is Na and Cl. I expect you to be able to look on the periodic table and get +1 and -1. So first step, we got metal and nonmetal. Second step, we write our charges, so that's already done there for you. Third step is we cross them over, so I'm going to get Na1, Cl1. Next step is to reduce the subscripts. So it's already reduced down. Basically, by reducing, we're looking to see if we can divide them by any numbers. And the last one is to remove any 1. So I'm going to have NaCl. So there's my compound. If I come to this one, I've already got the charges written up there. I've got metal and nonmetal, so I'm going to get K2S1. I don't want the 1, so I'm just going to get K2S. When you start getting the pattern, when you notice 1, so you don't need to write it. Next one, metal and nonmetal. Magnesium's in group 2, so plus 2. Oxygen's in group 16, so it's a minus 2. So we're going to crisscross this over. So I'm going to get Mg2O2. And these 2's can be reduced down. I can divide them both by 2, so I'm going to get MgO. It's very important that you do that because when you get to drawing bonds, it's going to be difficult. Next one, we're going to have Fe plus 4, O minus 2, so we're going to get Fe2O4. I can divide both of these by 2, so I'm going to get Fe1O2. And the last one here, I've got my charges already written up here, so plus 3 minus 2. I'm going to get Fe2O3. I can't reduce them down, so that's what I'm stuck with. So again, identify the metal and the nonmetal. Write down the symbol with their charges, so look up their oxidation number. Cross over the charges from top to bottom, and reduce subscripts and remove any ones. And we'll cover drawing bonds in another lecture here. Next thing that we want to do is naming ionic bonds. There's one thing that we always need to make sure that we do when we're working with ionic bonds is to identify if there's a transition metal or not. Again, the transition metals, when you're looking at the periodic table, kind of draw just a quick little sketch here. You have something kind of like this. You've got groups 1 and 2, and then groups 3 through 12 right here. That's where your transition metals are. There's a couple other ones that are floating around over here that are transition metals, specifically tin and lead. Those are transition metals, but groups 3 through 12. If you see any of those, you need to immediately stop and think about your rules. Okay, and then what you do is you list the cation. Again, the cation is your metal. So anything on the left-hand side of the periodic table, you're just going to write down the name. Second thing you're going to do is list the anion. Now this is important here, is that the name of the anion is the name of the element with the ending, okay, taken off. So we're going to take off the ending and we're going to add "ide" to it. So basically what it's going to look like is that we're going to have, let's say you're dealing with oxygen. You take the first syllable, so we'll take ox, and then I'm going to drop the GEN ending and I'm going to add "ide" to it. So that's kind of what we're doing here. So this chart shows us a lot of our metals. Hydrogen can do both things, so it can be the hydrogen or it can become hydride. But here's our metals: lithium, sodium, potassium, cesium, and so on. We're not changing those names at all. When we look at our anions, we have fluorine becomes fluoride, chlorine becomes chloride, bromine becomes bromide, iodide, oxide, sulfide, nitride, and phosphide. So you just kind of want to get in the pattern of hearing that. And anytime you hear the "ide" ending, you should immediately be thinking that this is some sort of bond. One last thing here is that the numbers do not matter at all when we're doing these things. So let's practice these. So we've got NaCl, so we look up Na, and that's and then we look up Cl, and that's chlorine. So we're going to take the first syllable, so we've got chlor, and then I'm going to add the "ide" ending to them. So we name it sodium chloride. Second one, we've got K, which is potassium. And the last one is sulfide. And then we've got magnesium. And we've got nitrogen, which becomes nitride. So fairly easy when there's not a transition metal. When there is a transition metal, we need to identify what its charge is. Those transition metals can have more than one charge. So we can have anything from +1 up to +6 very easily. So again, we do the same thing. We list the cation first, and we put the anion second. But in between these two, we're going to add in Roman numerals to tell us what the charge is. So here's an example down here. So I have zinc 3 oxide. So zinc 3 means, in this case, I have zinc, so Zn. And I put +3 over here, and then I've got O with a -2. Then I've got copper 2 oxide, so I'm going to put Cu And I put +2. This is telling you the charge. So each one of these Roman numerals is a charge. And then oxygen has a -2 charge. So when we put that on there, we get a -2. So looking at this right here, chromium is in the groups 3 through 12. So I'm going to put chromium. And then I show you the charge here so you know what Roman numeral to put in. So I've got 6. So there's the Roman numeral for 6. Oh, I'm sorry, that's 4. So chromium 6. And then chloride. Copper is also in those transition metals. So I've got copper. I put the Roman numeral 1 in there to represent its charge. And then I put nitride for nitrogen. Iron is also a transition metal, so I've got iron. I put Roman numeral 2 in there for its charge. And it becomes sulfide. So remember, when it's a transition metal, you always have to put in a Roman numeral to show you what the charge is. So just a couple real quick examples here. Pb is one of our transition metals that does not fall in groups 3 through 12. So I do need to label that. So that is lead, Roman numeral 4, sulfide. This next one, barium, is not a transition metal. Barium is in group 2, so I can just write barium. And then I just put oxide. I do not need a Roman numeral because it is not a transition metal.